Good afternoon, everyone. Welcome back to Digital Control System. The lecture that I will be covering today is discrete models of sample data systems. There are a few points for today. I will begin with Laplace transform of delay. First, let's take a look of step function. That is denoted by 1t. So 1 means final value is 1, step from 0. And the figure of step function is supposed to be like this. From 0 and then step to 1 without delay. What does the curve looks like when there is a delay? And here it is a specified unit delay. Okay. Unit delay means the delay only one time step, right? And as you can see the notation here. Let me review the expression in arithmetic form. 1 of t equal to 1 when t is greater than or equal to 0, and 1 of t equal to 0 when t is less than 0, negative. Okay. You can observe that t is the argument of the function. Arguments or input, right? For this one, similarly, maybe I should start from the arithmetic form. First, 1 of t minus t like this equal to 1 when the argument is positive or 0, which means t minus capital T greater than 0, like this, right? And for this, 1 of t minus capital T equal to 0 when t minus capital T less than 0. This means when t greater than capital T, okay, greater or equal to capital T, like this. This one I can write like this. So you can see here it is 1 when t taken from t to infinity, right? When this t greater than capital T, okay, greater or equal, it means it's step here, right? So from here the value of this function is 0 and then step to 1. Okay, so this is delay. Right, unit delay. And what about you have p step delay? What does this look like? Right. It means it step from so it step from to 1 at time pt, right? Here is delay. Okay. Next, let's see Laplace transform of delay. Let's see the Laplace transform of step function first. If you step at 0 like this, right? This is in time domain, and then to Laplace transform, you get 1 over s. How about this one? When it step here, it step here at the unit delay, right? Then what is the Laplace transform? So now I let you find Laplace transform of this, okay? Just to remind or recall the formulation, so you can warm up and you can remember easily once you get the result on your own. So let's take a paper and pen and try on your own. Okay, from the definition, Laplace transform of any function is equal to integral from 0 to infinity of any function, that function, time e to the minus st dt. Okay, but because the function is not 0 from capital T to infinity, then this integral is reduced to just integral from capital T to infinity, and the whole function here is just 1 here, become 1. After then we can easily integrate it and substitute by the final value T and infinity, you get the result. And now let's take a look the pattern, right? Pattern, this one you can say 1 of T minus 0, then you have 1 over s e to the minus 0s, right? You can say so. And this one 1 of T minus capital T, then you can have this. How about Laplace transform of 1 of T minus pt? Then it equal to 1 over s times e to the minus pts. Okay. The next point, I'm going to show you how to use Z transform for dynamical system. First, let's see a comparison between continuous and discrete system. First thing, they both represent dynamic system. Represent means you use a formulation to compute the output of the system from the known input, right? And the dynamic of continuous system is represented by transfer function that you obtain from Laplace transform, right? So Laplace transform used for analysis in continuous time, and Z transform used for analysis in discrete time. And here, let's take a look of a function. Actually, this function is RAM. Okay, RAM. First, this function is non-zero from 0 to infinity. Okay, from t taken from 0 to infinity. When you look at this curve, please just just see the continuous time, the lines. Ignore the dot line, the dot points. Okay, ignore the dots. I just make it for you easy to make it easy to compare between this and this. Actually, for continuous, you just have the solid line. And Laplace transform of this ramp is 1 over s squared, right? And for the discrete time of ramp, same ramp, but here you define it in a sequence. So this axis is k. You can count k from k equal to 0 here, k equal to 1 here, 2 here, or k minus 1 here, k minus 2 here. Okay? And actually these dots are on the same line. Okay? And then it's the transform is like this. Okay, so what I'm trying to confirm or to clarify with you here is that z transform of a particular function equivalent to its continuous version. Actually the value same if you evaluate at the same time. Okay, you have sample time t here. Okay, you have sample time. Let's say sample time is 0.1. Then here is 0.1. Here is 0.2. And if you evaluate at 0.2 second here, you get the same value. Okay. So, in some sense, we can interpret the function in the time domain by two ways. One is for a continuous version, and another one is for discrete version. And let's see the application of the transform for a dynamic system. Suppose you have a dynamic system, let's say RLC circuit or DC motor, okay, or any other system that is linear. Then you use Laplace transform to find the transfer function here, where the input here is continuous and output also continuous. Okay, here is output. But then when you want to use computer to compute the system, or even in practice you use computer to compute based on third-hand controller to have the output converge to desired. Okay, so when you apply it with digital computer, you need to sample for on the output. You sample data point at a specific sample time in order for our controller to compute the control action. And from the input, so the computer compute at sample time. Okay, it can compute the control action at particular time, right? KT here. But of course, you cannot just have sample time at particular time for your continuous system, because your original system is continuous. So in the discrete sense, you just try to use some tools in order to compute when you get the result, and then you need to find a way to inject the input into your system as a continuous form. Here you can see control engineer can use some devices. For example, this one is analog to digital converter in order to sample data from the output. And for this one, they use digital to analog converter. Digital means only sample point. For example, if your input is like this, your control action of continuous version is like this, then the sample that the control action that you get from computer only point here and then point here and then point here and then point here, then point here and then point here like this, right? And then you need to make it continuous for your continuous system. Then one method is called zero order hold. Okay, now you hear zero order hold. Order. Zero order hold means the slope is zero, so it's hold like this until it get the new value, so it update to the new value, and then it hold the value here until it get the new value here, right? It just keep holding like this. It holding between sample time, okay, like this. So the stair-like curve is the control action from controller plus zero order hold method. Okay, while the continuous the control action from continuous version is this curve. All right. So let's compare. If you inject one input as continuous like this, yeah, like here, and another case you inject the stair-like curve of the control action, then of course you get different result of the output, right? Yeah. And now we are looking at how to analyze the result of the output when you inject the stair-like control action. Okay. Now let's see the stair-like control action in just during one period, one sample time, okay, or one time step from 0 to capital T. When you look at this input, it is just pulse. It's called unit pulse. Okay, unit pulse. Unit pulse. This unit pulse, if you look at clearly, well, I complete the drawing. Actually, it's 0 from here, and then it jumped to 1 here. Okay, it jumped to 1 here, and then it jumped back to 0 here. If you look at carefully, you can see the step time, step of different value twice. First, it step from 0 to 1, and then it step from 1 to 0. You can see 2 steps. Yeah, that's why it's easy to construct unit pulse by using step function. This one step, this one is another step function. But this one, you step up, right? From 0, you step to 1. And then you keep like this, and then you step from 1 to 0. It is the same as step from 0 to 1, but with the negative sign. Correct? Yeah, so, well, I would say, let's say you have another step function that it keeps 0 like this, but then it step down like this. It's like you have one step function with negative sign. This is what I want to say, right? So let's check together whether this is really this one really represent this unit pulse. Okay, let's see t less than 0. This one is 0. This one also 0. So checked this part. And what about t in between 0 and capital T? This one is 1. How about this one? This one is still 0, right? So the result is 1. How about T greater than capital T? This one is 1. This one is also 1. Then 1 minus 1, you get 0. So it means it falls back to 0 here. Okay, now we have the input as unit part like this. Then we want to check for each unit part what is the how the output look like. I mean, what kind of formulation can be used to formulate the output when you already know the transfer function as GS, right? When you have GS, and if you just have input as continue like this, then you just got GS over S as a transfer function of the output, right? Because let me remind here, review a little bit. Y1 of S equal to G of S times U of S, right? So if U of S is just step continuous like this, then its transfer function is just 1 over S, right? So you got G of S times 1 over S here. It's just from there, right? This is just from there. But now we only take one unit pulse, right? Just one unit pulse, and so the input is like this. The input is like this, and then we can use the Laplace transform of the input. So this one Laplace transform of unit pulse. So when I use Laplace transform, then I can have unit pulse as what? This one is 1 over S, right? How about this one? 1 over S e to the minus Ts that you just found earlier, right? And now because the output equal to input time transfer function, this is transfer function, and this one is from input of unit pulse. Okay, so this one is this one, right? Like this. Any question? Okay. So next let's find Z transform of the output. Z transform of the output in terms of sample time KT, right? In discrete time KT. And well, actually Y1 the discrete time of output is just the same as the continuous time, but we evaluate at particular sample time, right? Just points like this, like this, and this one. So this value is the same as this value. This value here is the same as this value here, right? So Z transform of discrete time here is just Z transform of Laplace inverse of the continuous transfer function, because Laplace inverse of this one you can have y1 of t, but you sample t to be kt, right? And then, well, inverse is just one operation to a particular function, right? Operation means you just apply integral, right? Because Laplace inverse also some type of integral, Cauchy integral, for example. And now you apply Z transform another operation to that. So in here, operation and operation, then you just simplify just one operation. It means, well, you apply operation Z transform to the Laplace transform of output itself. So the notation here is just to make it abstract, more abstract, but in the sense that you apply Z transform to the Laplace transform of the function y. Okay, it's not any complicated mathematics that need to derive. Okay, it's just abstract thinking of applying operation. Okay, a certain operation. Then you substitute y1 of s from the previous slide here. Okay, and let's take a look at it closely. You can see that actually this is just two parts, right? The sum of two parts when you distribute this one to one here and then this one to this term here, right? And for the second part, the Z transform of the second part can be simplified to be like this. Actually, Z transform of this one is just unit delay, and this is unit delay. You learned before from Z transform, right? Just unit delay, and then Z transform of this, and from this one, if you know the exact G of S, then you can use tables because table already compute for certain function for us. We don't need to compute again. But if you want to warm up, when you know G of S and then you want to try by yourself, you can. So finally, we can have the formulation of Z transform of a dynamic system, particularly a transfer function, can be computed in this way. Okay. Well, but don't forget, you find Z transform of your system that you apply zero order hole at the input. Don't forget, you apply control system. You compute the control action from digital computer, and then you apply zero order hole. Then you can find the Z transform for that control system. Okay. Any question? If no, then you can have a break for 5 minutes.